Hello lovelies, in this video we're going through everything you need for your AQA GCSE Physics Paper 2, and this is to a grade 9 standard. So we're going through point by point, showing you how to lay things out in the exam to make sure you are aiming for those top marks, that grade 7, that grade 8, that grade 9. Now, after you've done this, you can jump down to the description, you can have a look at the free questions, the free flashcards that are over on the website, and you can go and have a look at the predicted papers and the walkthroughs of the predicted papers that we've done for this year.
In physics, we learn about scalar and vector quantities. A scalar is a quantity which has magnitude only, so it only has a size associated with it, whereas a vector has both that magnitude but also direction. So in physics, we might often see vectors represented using an arrow, and the size or length of that arrow gives us an idea of the size of the quantity, and the direction it's pointing tells us the direction of it. Now at GCSE, of course, we learn about so many different things. Now, I've got this little table here just to summarise whether certain things you've learnt about are scalar and vector. So we need to know that speed is a scalar, whereas velocity is a vector. Distance is a scalar, whereas displacement is a vector. Time and energy are both scalar quantities as well, because they just have a size associated with them, not a direction. Whereas acceleration, force and momentum, all of these things we will learn more about, are all examples of vectors. All forces are either contact forces or non-contact forces. Contact forces are experienced when objects are physically touching. Some examples of this include friction, where things are rubbing against each other, air resistance, where the air is in contact with you, tension, and also the normal contact force. And there's loads of other ones too. Non-contact forces, on the other hand, though, involve objects that are not physically touching. They're physically separated, and yet they're still experiencing a force between them. So some examples of this include magnetic forces. If you've ever held two magnets together, you'll be able to feel, even though they're not touching them, pulling together or pushing apart, even though there's no physical contact. As well as this, we have electrostatic forces and also gravitational forces. Now, don't forget that force, whether we're talking about contact forces or non-contact forces, are vector quantities. So they always have the magnitude, but also the direction. The weight of an object is the force acting on it caused by gravity. That means that the weight of an object is dependent on the gravitational field strength. In fact, if we were to have our weight on planet Earth, then we were taken to the moon or something which has a smaller gravitational field strength, our weight would decrease. We need to know that the weight of an object is directly proportional to the mass of an object. And the equation that links them is weight equals mass times gravitational field strength, where weight is actually a force measured in newtons, mass is measured in kilograms, and G, or gravitational field strength, is measured in newtons per kilogram. Now, a really common misconception, and it's because of our everyday language, is that our weight is the same as our mass. But it isn't at all. And actually, when we say that we weigh ourselves or we weigh this amount, that's incorrect. It's actually our mass that we are talking about. So we need to get our head around the fact that in physics, weight is the force in newtons. If we want to measure the weight of an object, we would use something called a Newton meter or a calibrated spring balance. It's also important that we know that weight is considered to act at a single point, the centre of mass of an object. Lots of forces can act on an object. However, we can replace all of these different forces with just a single force called the resultant force. Now, the resultant force is just a single force that has the same effect as all of the original forces acting together. Let's have a look at what that means. So if we had a 4 Newton force, and we added another 4 Newton force in the same direction to it, there would be a resultant force equal to 8 newtons in that same direction. However, if we had a 6 Newton force, and it was encountering another 6 Newton force, but in the opposing direction. Because force is a vector, we could say that this is actually minus 6 newtons. What's going to happen then is these two forces are going to cancel each other out. And so actually the resultant force is equal to 0. Make sure that you can do these yourself as well, because they could ask very similar questions in the exam. A single force acting at an angle can be resolved into two components that act at right angles to each other. So this diagram that I have here shows that. This diagonal force, which is acting of course at this angle here, can be split into this horizontal component and this vertical component. Now these two components have the same effect as the original single force. Now when we draw these diagrams, it is very important that we make sure that we draw these arrows in the tip to tail formation. So this horizontal one that we have here, tip is here, and then we put the vertical component that makes that overall resultant force so that the tail of it, the end of it, is touching the tip of the other. Now remember that this resultant force here is not an additional force that adds up with the other two. Instead, that is the overall force of those horizontal and vertical components. Now, we can actually do this the other way around too. We can work out the resultant of two forces that are at right angle to each other. We can do this by drawing a scale diagram. So we can get a ruler, work out what scale we want to use, and draw the horizontal component. So say if we had something that was, 6 newtons, we could draw something that's 6 centimetres long perhaps. Then if we had a vertical component that was 8 newtons long, we could do something that's 8 centimetres long in that vertical direction at the end of our 6 Newton force. Then we can draw a line to connect the two, which would be this pink line that I have here, measure this line and use the scale to determine the resultant force. So in this case, if we were using that scale, then we could measure this pink line and we'd see that it's 10 centimetres long. So therefore it is 10 newtons. And that is how we can use scale diagrams to work out resultant forces. We also need to make sure that we can draw some free body diagrams. Now, a free body diagram is a diagram that we use to describe situations where there are several forces acting on an object. So here we have an example of a free body diagram on an accelerating car. Here we can see there's 4 different forces acting on the car. There's the weight which acts down, the normal contact force acting upwards, the resistance due to friction and air resistance going in the opposite direction to its motion, and the thrust going forward. Now here, if we look at these forces, the up and the down forces are balanced. There's no resultant force in the up and down direction. However, we can see that the thrust arrow is bigger than the resistance arrow. Now that means that we have a resultant force in the forward direction. Now if all of these forces in all directions were balanced, then there would be no resultant force. And that means that the object would be stationary, or if it was already in motion, it would continue at a constant speed. A force does work on an object when the force causes the object to move through a distance. The work done by a force on an object is given by work done equals force times by distance, where work done is measured in joules, force is measured in newtons, and distance is measured in meters. Of course, as always, we could use a little cheeky triangle here if you struggle with the algebra. If not, I would always recommend that you just rearrange this using the algebra that you've learnt in maths, but it's always good to have something up your sleeve in case you get stuck. If you did use a triangle, I would just pop a W on the top for work done and force times distance on the bottom. Now, we need to know that 1 joule is equal to 1 Newton metre. And this is because 1 joule of work is done when a force of 1 Newton causes a displacement of 1 metre. It's also really important that we know that work done against friction will result in a temperature increase. And this is why if you rub your hands together, they start to get warm, because you've done work against friction. When a force acts on an object, the object may bend, compress, or stretch. or some combination of all of these changes. To change the shape of a stationary object, there must be more than one force acting on the object, like you can see in these diagrams here. So for example, to squash a plastic bottle, we must push the sides of the bottle together. Changes in shape are called deformation. And we need to know about two types of deformation, elastic and inelastic. Now this table here summarises the differences between those two. Elastic deformation is reversed when the force is removed. For example, an elastic band that gets slightly stretched will just ping back to its original shape when you remove the force. Elastic deformation, on the other hand, is not fully reversed when the force is removed, and we see that there's been a permanent change in shape. A good example of this is a plastic bottle that's been squashed, or even perhaps an elastic band that you'd stretched too far and now it's no longer stretching back. The extension of an elastic object is directly proportional to the force applied to it, provided that the limit of proportionality is not exceeded. Now this is called Hooke's law. The force applied to extend an elastic object by an extension E is given by force equals spring constant times by extension, or F equals K times E, where F is the force measured in newtons, K is the spring constant measured in newtons per metre, and E is the extension measured in metres. Now this relationship also applies to springs that are compressed. However, in this case, the E isn't going to be the extension, it's going to be the amount that the object is compressed. So now let's think, if we plot force against extension, we will expect to see, if Hooke's law's being obeyed, this direct proportion, this straight line. It will go through the origin and it will have this constant gradient. And in fact, we can calculate the spring constant by finding the gradient of this line, so the change in y over the change in x. The limit of proportionality is the point at which Hooke's law is no longer obeyed, and the extension is no longer directly proportional to the force applied. Now we can really clearly see this on a graph. As you can see here in this graph, you can see we've got a straight line for the first part of it, so this region here. However, beyond this limit of proportionality, we no longer have that linear relationship between force and extension. And that is when we know we have exceeded that limit of proportionality. So the elastic limit of a material is the furthest point it can be deformed and still be able to return to its original shape when that force is removed. And when a material passes its elastic limit, its deformation becomes inelastic. When a spring is compressed by a force, work is done on the spring and elastic potential energy gets stored in that spring. Now the elastic potential energy stored in a stretched spring is given by elastic potential energy equals half times the spring constant times by extension squared, or EE equals a half times K times E squared, where our elastic potential energy is measured in joules, the spring constant is measured in newtons per metre, and the extension is measured in metres. Now if the spring has no inelastic deformation, we can say that the work done is equal to the elastic potential energy. A lever consists of three things: a pivot, an effort, and a load. However, these can all be arranged in different ways. For example, in some scissors, we have the effort, which is our force that we push down on the handles. Pivot is in the middle, and the load is at the end on those blades. Wheelbarrows, on the other hand, have the pivot, followed by the load, which would be the weight of our contents of our wheelbarrow, and then the effort, which is our force of our hands lifting up that wheelbarrow. Now, levers can act as force multipliers. They allow us to lift heavier loads than the effort force would normally allow, so they're really, really useful. Now, longer levers increase the force exerted on a load. And a typical example of this is using longer spanners compared to short ones to turn a nut. It's just easier. Another example would be using a wheelbarrow with a longer handle compared to a shorter handle. This is also going to increase the force exerted on the load, making it easier to lift a heavier load. Now, an object can rotate if a force or a system of forces is exerted on it. And we call the turning effect of a force the moment of a force. Now we can calculate the size of the moment using this equation here. Moment of a force equals force times by distance. Now in this case, the distance that we're talking about is the perpendicular distance from the pivot to the line of action of the force. Okay, so make sure that you've got it at right angles to that force. Now the moment is measured in Newton meters, force is measured in newtons, and the distance is measured in meters. If an object is balanced, it is in equilibrium. So in that case, the total anti-clockwise moment about a pivot is equal to the total clockwise moment about a pivot. Now, in a question like this, if you had to do some calculations, make sure you work out which forces will be making it turn in a clockwise or an anti-clockwise direction, and then work out the moments of all of the clockwise moments, all of the anti-clockwise moments, then add all the anti-clockwise moments and set them equal to the sum of all of the clockwise moments. Okay, so that's a really, really important rule we need to know, but it's all about things being balanced again, exactly like the seesaw, like you see here. If you imagined it balanced, it's because the anti-clockwise moments about that pivot would be equal to the clockwise moments about the pivot. A gear is a wheel with a toothed edge, like you can see in these diagrams. Now the teeth of one gear is able to connect to the teeth of another gear, and therefore as one gear turns around an axle, the other will also turn. Now it's important that we know that connected gears, like you can see in this diagram here, will rotate in opposite directions. As you can see here, if one of them is rotating in an anti-clockwise direction, the other one will rotate in the clockwise direction. So make sure you know that key fact as to what a gear is and how it works. A fluid is a substance that can flow, so this includes liquids and gases. Now the pressure in fluids cause a force at right angles to a surface. We might hear this called the normal to a surface. Now the pressure at the surface of a fluid can be calculated using this equation here. So the pressure is equal to the force normal to the surface divided by the area of the surface. That is just P equals F over A, where pressure is measured in pascals, force is measured in newtons, and area is measured in meters squared. The pressure caused by a column of liquid is given by pressure equals height of column times density of liquid times by the gravitational field strength. Now we might see this as P equals H times by the Greek symbol rho times by G, where pressure is measured in pascals, the height of the column is measured in meters, density is measured in kilograms per meters cubed, and gravitational field strength is measured in newtons per kilogram. Now, when an object is partially or completely submerged in a fluid, it's experiencing a greater pressure on its bottom than its top. Now, this pressure difference creates an upwards resultant force on the object. This force we call upthrust. Now, if the weight of an object is greater than its upthrust, it's going to sink. However, if the weight of an object is equal to the upthrust, it will float. Now, whether an object will sink or float depends on the density of the object. The upthrust of an object in a fluid is equal to the weight of the fluid that it displaces. Now, if an object is more dense than the fluid, then it will sink. And the reason for this is the weight of the object is going to be greater than the weight of the fluid displaced. This means that the weight of the object will be greater than the upthrust. Now, if an object is less dense than the fluid, it's going to float to the top. Now, this is because the weight of the object is less than the weight of the fluid displaced. And so the weight is less than the upthrust, and it floats. If a column of water has several holes at different heights, we can actually observe the differences in pressure. Now, water from the bottom of the column is going to spurt out at higher pressure, and as a result, it's going to travel further than the water from the top of the column. Now, this is because pressure in the column of water depends on height, and therefore how much water is above it. The Earth is surrounded by a layer of air called the atmosphere. Now, as air, together with all gases and liquids, is a fluid, the atmosphere has a pressure associated with it, and we call this the atmospheric pressure. Now, atmospheric pressure gets caused by air molecules in that atmosphere colliding with surfaces. Atmospheric pressure decreases with height. We need to be able to explain why atmospheric pressure acting on a surface does decrease with height. So, there's a couple of reasons here that we need to pull together. Firstly, as height increases, there's going to be fewer air molecules above the surface that we're looking at. So the higher you get, the less air is above us. On top of this, as we get higher and the altitude increases, the density of the air also decreases. So firstly, we have the fact that density is less, but then also the fact that as we get higher, a bit like moving from the bottom of the ocean where you've got so much ocean on top of you, and then swimming towards the surface where there's less ocean on top of you, there are going to be fewer air molecules on top of us as we go higher. So the net result of all of these factors is that the weight of the air above the surface that we're looking at here is going to decrease with altitude, and that is why atmospheric pressure decreases with height. In physics, we're going to see the words distance and displacement used really often. However, to your everyday person, you probably wouldn't think there's any difference between the two words. However, there is, and we need to know that difference. So distance is a measure of how far an object has moved. However, it gives us no information at all about the direction that the object has moved. Now, for this reason, distance is a scalar quantity. Displacement, on the other hand, tells us the distance an object has moved, but it also tells us the direction that it has moved in. That means that displacement is a vector quantity. Speed is a scalar quantity. That means that it does not have a direction. The speed a person can walk or run depends on lots of different factors, such as age, fitness, distance travelled, and terrain. However, unfortunately, we need to know an approximate average speed for certain different activities. We need to know that when walking, the average approximate speed is 1.5 metres per second. When running, the average approximate speed is 3 metres per second. And cycling, the average approximate speed is 6 metres per second. So make sure you learn those key facts. The speed of sound and wind can also change dependent on the conditions. We need to know that the typical speed of sound in air is 300 metres per second. The distance travelled by an object moving at a constant speed for a specific amount of time is given as distance travelled equals speed times time, or S equals V times T. Now, of course, if you're not too confident, you could always turn this into a nice little triangle. This is going to look something like this, where the S is going to be on the top, and then you have V times T on the bottom. So long as you get the marks, I am happy. So remember, distance is measured in metres, velocity is measured in metres per second, and time is measured in seconds. Now, velocity is a vector quantity. Velocity is just the speed in a given direction. When an object moves in a circle at a constant speed, a bit like a planet orbiting the sun, the direction of its motion is actually constantly changing. Now, this means that although the speed isn't changing, the velocity is also constantly changing. Remember that velocity is the vector version of speed, and it has magnitude and direction. So, because the direction changes, even if the magnitude doesn't, the velocity is always changing. If an object moves along a straight line, the distance travelled can be represented by a distance-time graph. The gradient of that distance-time graph gives us the speed of the object. And if the graph shows a straight line, like we can see in this diagram, we know that the object is moving at a constant speed. And the steeper the line, the faster the speed. However, if the curve on the distance-time graph slopes upwards and the gradient is getting steeper with time, we can see that the object is accelerating. On the other hand, if the curve on the distance time graph slopes downwards and it gets less steep over time, then we can say that the object is decelerating. Now, if we have one of these curved distance time graphs, we can still work out the speed at a particular time. We can't do it as simply as just working out the gradient of the line. What we need to do first is draw a tangent to the curve at the point we're being asked about. So here, if it was this particular time here, so let's call that, 5 seconds, we would then draw the tangent at that point, like I have here in this diagram. Make sure I use a ruler and a pencil to draw a straight line just touching the curve at that point. And then I will make a little triangle where I have the change in y and the change in x. And I would work out the gradient by saying that it is equal to the change in y over the change in x. And that is how we can work out the speed at any point on this curve. Average acceleration of an object can be calculated using acceleration equals the change in velocity over time taken. We could see it written as A equals delta V, where the delta means change, over t. So the acceleration is measured in meters per second squared. The change in velocity is just measured in meters per second, just like any old velocity, and time is measured in seconds. Objects that are slowing down are said to be decelerating, and an object that is decelerating has negative acceleration. Remember, acceleration is a vector. The fact it can be positive or negative gives us that direction of the acceleration. If an object moves along a straight line, the velocity can be represented by a velocity time graph. Now, the gradient of the velocity time graph gives us the acceleration of the object. If the graph shows a straight line, then the object is moving at a constant acceleration. And of course, the steeper the line, the greater the acceleration, because we've got this larger gradient for steeper lines. Now, if the curve on a velocity time graph is curved, then the object's acceleration is changing. If, however, we have a horizontal line on a velocity time graph, then that tells us the object has constant velocity. The distance travelled by an object can also be found on a velocity time graph simply by calculating the area. Now, in simpler velocity time graphs, that area can be found just by simply breaking it down into shapes. Like in this diagram that we have here, I can see that I've got a triangle. So I can work out the area of that triangle by using half the base times the height. However, in harder velocity time graphs, where we have a curve instead, we may need to count the squares that we can see underneath that curve to work out the area and therefore the distance travelled. So keep an eye out for those. So in summary here, the acceleration can be found using the gradient on a velocity time graph, and the distance travelled can be found using the area under that velocity time graph. If an object moves through a fluid, a gas or a liquid, initially it's going to accelerate just due to the force of gravity. However, as it falls, resistive forces will start to increase, until eventually that force of gravity, the weight, will become balanced with those resistive forces. This means that there's no overall force, no resultant force, and terminal velocity has been reached. Now, all that terminal velocity means is it's that constant velocity it is now falling under. So make sure that you familiarise yourself with this phrase of terminal velocity and you understand what it means. This process of terminal velocity being reached can be represented using a velocity time graph. So we can see that when initially this thing starts to fall, the body is initially simply accelerating due to the force of gravity. In that split second it starts to fall, there's no other forces acting on it. However, as this object begins to fall, over time resistive forces will increase. The more it falls, the more air particles are going to be hitting it. This means that the resistive force increases. However, the weight will still stay the same. It's still the same object that weighs the same amount. Now, the result of this is that the resultant force is going to decrease. And because force equals mass times acceleration, the acceleration is also going to decrease. Now, as this object continues to fall, the resistive forces are going to get bigger still. The faster it moves, the more air particles it's moving through, and therefore the more air resistance it has. Until eventually, those resistive forces are so big that they are equal to the weight. Now, at this point, the resultant force is zero, and this is because the forces are balanced. Now, if the resultant force is equal to zero, because force equals mass times acceleration, we also have zero acceleration, which means that we have a constant velocity, which we call the terminal velocity. Newton's first law states that if the resultant force on a stationary object is zero, the object will remain stationary. However, if the resultant force on a moving object is zero, the object will continue moving in the same direction with the same speed. When we have an object moving at a constant speed, the driving force will be balanced by resistive forces such as the friction and the air resistance. That's what gives it that resultant force of zero because they're balanced, and therefore it just continues in the same direction with the same speed according to Newton's first law. Newton's second law tells us that the acceleration of an object is directly proportional to the resultant force acting on the object and inversely proportional to the mass of the object. Now, as a little top tip, make sure that you remember that this symbol here represents proportionality, looks a bit like a little fish, and this like squiggly equals sign means approximately. Now, Newton's second law gives us this very important equation. Resultant force equals mass times acceleration, or F equals m times a. Remember, we could use a triangle if you find it difficult to rearrange these equations, anything that's going to get you the marks. If we did use a triangle for this, then we would put the F on the top and the m times a on the bottom. Don't forget that force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. We need to make sure that we know the difference between inertia and inertial mass. So inertia is the tendency of an object to continue in their state of rest or of uniform motion, whereas inertial mass is the measure of how difficult it is to change the velocity of an object, and it's the ratio of force over acceleration. Newton's third law tells us that when two objects interact, forces that they exert on each other are equal in magnitude and opposite in direction. So here, let's have a look at this diagram here. A man is pushing on a wall, so he's got the force of his push. However, the wall is going to exert an equal and opposite force back on that man, and that is showing us Newton's third law. Stopping distance is the sum of the thinking distance and the braking distance. So it's the distance in total that it takes for you to stop from the moment you see an object to the moment you stop, okay? So the thinking distance is the distance that the travel thinks during the driver's reaction time. So imagine you're driving along and you see a rabbit run into the road. The thinking distance will be the distance that you travel between the moment you see that rabbit to the moment you put your foot on the brake. And then the braking distance is the distance the vehicle travels under the braking force. So that is the distance you travel from the moment you put your foot on the pedal to the moment you're stationary. So for a given braking force, greater speed is going to cause greater stopping distances. The typical reaction time of a person is between 0.2 seconds and 0.9 seconds. Make sure you learn that fact. Now, there's a few things that can affect the reaction time of a driver, and therefore the thinking distance travelled. The reaction time can get affected by tiredness. The more tired you are, the longer your reaction time, the use of drugs, the use of alcohol, and also the presence of distractions. So for instance, loud music, things like this can distract you and increase the reaction time of the driver. We need to be able to describe a method to measure human reaction times. So here we go, okay? So first up, ask a person to sit at a desk with their hand out. Hold a ruler up to their hand and line up the 0 on the ruler with the person's thumb and forefinger. So now you're going to tell the person that when the ruler gets released, they need to catch it as quickly as possible. So now we're going to drop that ruler, but we're not going to tell the person. And we're going to measure the distance travelled by the ruler in this time before they can stop the ruler. So now we have enough information to calculate the final velocity of the ruler. We can use the equation for constant acceleration that states that v squared equals u squared plus 2as. We know that u is equal to 0 because it started stationary. S is the distance travelled by the ruler that we measured. And a is the acceleration caused due to gravity, which we could use 9.8 metres per second squared or 10 metres per second squared. A question would give you a number to use if you needed it. So now you're going to use that equation to find v, and once you know what v is, you can calculate the time taken using the equation that says that acceleration equals change in velocity over time. Of course, we'll need to rearrange it to get time as the subject. Time would be equal to change in velocity over acceleration. But once we've done that, we can just substitute in the values that we already know to get that time. So once we do that, we will finish off by carrying out some repeats and calculate a mean. To ensure this experiment is calculated correctly and we're actually just working out those human reaction times, we need to make sure that we carry this out in a room with no distractions that's going to affect that reaction time. The braking distance of a vehicle is affected by the road and weather conditions. So if we have poor road and weather conditions, such as icy or wet roads, we're going to increase the braking distance. Braking distance also affects on the vehicle conditions. So if we have poor vehicle conditions, such as worn tyres or worn brakes, again, we're going to increase the braking distance of the vehicle. Now, velocity also affects braking distance. And we need to know very particularly that if velocity doubles, the stopping distance actually increases by a factor of 4. It doesn't just double 2, it increases by a factor of 4, so make sure you know that. Now, when a force gets applied to the brakes of a vehicle, work is done. Now, the friction between the tyres and the brake pads causes the kinetic energy of the vehicle to decrease and the brake pads to increase in temperature. Ultimately, the faster the vehicle travels, the greater the braking force required, and therefore the greater deceleration that we have. Now, of course, we need to know, well, what is dangerous about a greater deceleration? We need to know that the brakes can overheat under these conditions, and the driver may lose control of the vehicle, so make sure you know those dangers. Momentum is a property of moving objects, and we can calculate the momentum of an object of mass m travelling at a velocity v using the equation that states that momentum equals mass times velocity. We sometimes refer to momentum using the letter p, so we could say that p equals m times v, where the momentum is measured in kilogram meters per second, mass is measured in kilograms, and velocity is measured in meters per second. Now in GCSE, we're often going to hear about the conservation of momentum, and we need to know what that is. So we need to know that the conservation of momentum tells us that if we have a closed system, the total momentum before an event will be equal to the total momentum after the event. So for instance, in this diagram here, if we had two different objects that were about to collide, you could work out their individual momentums, add them together, and that would be equal to the total momentum that they have after the event. So we can do exactly the same there. The thing to make sure of is that when they're moving in an opposite direction, like we have here, we would use the velocity as a negative value. Remember, velocity is a vector, which means that it has a direction, and that direction generally shows itself as being positive or negative. So in this case, both of these objects moving backwards tells me that they have a negative velocity, and so I would be sure to use that in my calculations of momentum. So don't forget, the total momentum before an event is equal to the total momentum after an event in a closed system. Another key fact is the fact that momentum is another example of a vector quantity. It has a magnitude, a size, and a number associated with it, and it also has a direction. So we can also get negative values for momentum, which would show the direction of the momentum. When we have a collision, we experience a change in momentum. And as a result of this, the force exerted in that collision is equal to the rate of change of momentum. This equation here shows that. We know that force is equal to change in momentum divided by the time taken. We could see this written as F equals m times by delta V over t, where force is measured in newtons, mass is measured in kilograms, change in velocity is measured in meters per second, and finally time is measured in seconds. Many car safety features aim to increase the duration of that change in momentum, because the knock-on effect of that is that if we increase the time, we're going to decrease the force. So some examples of this include crumple zones, seat belts, and airbags. So we need to think, well, how does a crumple zone decrease the force in a collision? Well, first step is the car is going to crumple on the impact. This increases the duration of that collision. However, the change in momentum has remained the same. It was still going at the same initial velocity, and it ended at 0. This is going to decrease the rate of change of momentum because we're dividing that change of momentum by a bigger number, making it smaller. This decreases the force. And so this works exactly the same with seatbelts and airbags. We just, instead of saying that the car will crumple on impact, we might say the seatbelt will stretch or the airbag will compress. But we can use the same explanation in each of them. Waves can be described as oscillations or vibrations about a point. The direction of the vibration can differ, and this is what determines the type of wave. Waves can be transverse or longitudinal, and in a transverse wave, the vibrations are at right angles to the direction in which the waves transfer energy. However, with a longitudinal wave, the vibrations are parallel to the direction in which the waves transfer energy. Now, this can be a bit confusing. If instead we think of it in terms of a long spring like a slinky, and we think, what can we do with this slinky to turn it into a transverse wave or a longitudinal wave? And if we wanted to make a transverse wave, we would want to take that slinky and move it up and down and up and down and up and down. Now, if you think about it, the waves are moving forward, but the vibrations, your hand, are at right angles to that forward direction. Longitudinal waves, on the other hand, if you had that same spring or slinky and you wanted to make a longitudinal wave, you would bump it back and forth with your hand. And there, your vibrations, that movement of your hand, is parallel to the direction in which the waves transfer energy. Now, for ripples on the surface of water and sound waves in air, we need to know that it's not the water or the air that's travelling, it is the wave. So if we think, for example, about a stone that is dropped into water, we can see that ripples are produced. However, neither the water nor the stone move with the ripples. It's just the wave. If we also think about someone speaking, in this case, the voice box will be vibrating, making sound waves that will travel through the air. However, that air is not moving. We need to ensure that we can label a transverse wave and recognise its shape. So the transverse wave, as you can see here, looks like your very typical wave, up and down and up and down. Now, the tops of each of these waves is called the peak, the bottoms are called the trough. The height from the equilibrium position to the peak or the trough is called the amplitude. Make sure that you don't say it's from the peak to the trough. That's a very common mistake. And the wavelength is the distance between two identical points on the wave. Now, an easy way to do this is going from peak to peak or trough to trough. So here, another wavelength that we could draw on would be this position here. It is identical to the wavelength labelled on this diagram, but perhaps it's an easy way to identify it. So some mechanical waves are transverse, for example, water waves and seismic S waves. In addition to this, all of the electromagnetic waves that we will learn about in more detail, for example, ultraviolet and infrared, are all transverse. Now, longitudinal waves look like this. Longitudinal waves have compressions, which are regions of high pressure, where the particles are close together. And they also have rarefactions, which are regions of low pressure, where the particles are far apart. Now we'll find that some mechanical waves are longitudinal. These include sound waves, ultrasound, and also seismic P waves. We need to make sure that we can describe waves in the following terms. We need to make sure that we know that amplitude is the maximum displacement of a point on a wave from its rest position. The period is the time it takes for a wave to complete one cycle. Wave speed is calculated using wave speed equals frequency times wavelength. Frequency is the number of waves passing a point per second, and wavelength is the distance between a point on one wave and the next point on the same wave. Now, wave speed is the speed at which energy is transferred through a medium. And, as we've seen, we can calculate this using the following equation. Wave speed equals frequency times by wavelength, or V equals F times lambda, where lambda is a Greek symbol used to represent the wavelength. Now, wave speed is measured in meters per second, frequency is measured in hertz, and wavelength is measured in meters. Now, if you're doing physics instead of combined science, we also need to know that when waves travel from one medium to another, the wave speed and the wavelength may change, but the frequency will always stay the same. The period of a wave can be calculated using the frequency of the wave. So period is equal to 1 over the frequency. This can be written as T equals 1 over F. Don't forget that the period is the time it takes for a wave to complete one cycle. So period is measured in seconds, whereas the frequency is measured in hertz. It's also important that you remember that we might need to find the frequency given the time period. Now, if this was to occur, we would simply rearrange the equation, and this would look like F equals 1 over T. So a really easy one to rearrange there. Now, we might be asked how to measure the velocity of sound in air. Now, an experiment that we could do to do this would be to have two people stand a large distance apart, for instance 100 metres, use a trundle wheel to measure that distance between them because it's too large to use the metre rule. Now get one of these people to make a loud noise. So perhaps they could bang together two wooden blocks or bang together some cymbals. And the other person is going to have a stopwatch. And you're going to ask this person to start the stopwatch when they see the person make the noise, and then stop it when they actually hear it. Then we're going to repeat this experiment and take an average, take the mean. We're going to use the following equation now to calculate the speed of sound in air. So we know that wave speed is equal to distance, which could be that 100 metres, and then we divide it by that mean time that we calculated it takes for the person to hear the noise. We could also be asked how to measure the velocity of ripples on water surfaces. So to do this, set up a ripple tank and add water to it to a depth of about 5 centimetres. Now we want to adjust the height of the wooden rod so that it is just touching the surface of the water. Now we're going to turn on the motor and the lamp so that we can observe low frequency waves. Now we want to measure the length of several waves and divide by the number of waves to find the wavelength. This is going to be more accurate than just measuring one wave. Now we want to count the number of waves that pass a point in 10 seconds and divide by 10 to find the frequency. Finally, we can use the equation that wave speed equals frequency times by wavelength to calculate the wave speed. Waves can get reflected at the boundary between two different materials. When sound waves get reflected, we call this an echo. Now, the law of reflection, and this is important, states that the angle of incidence is equal to the angle of reflection. However, it's really important that you know that we measure these angles from the normal, which is this dotted line, as you can see in the diagram, which is at right angles to the surface. A very common mistake would be to measure that angle from the surface instead. So make sure you know the law of reflection and make sure that you can draw on the line of reflection if you know the angle of incidence. Now, when a wave meets a boundary between two different materials, it may behave in some different ways. Some of these ways are reflection, absorption, and transmission. So reflection is when the waves bounce back from the surface. Absorption occurs when the energy of the wave is transferred into energy stores within the material it's travelling into. And finally, transmission is when the waves continue to move into the substance after they cross that boundary. Sound waves are longitudinal waves. They travel through solids and cause vibrations in the solids. Sound waves can also travel through air, gases, liquids, anything that has particles. However, they cannot travel through a vacuum because there are no particles in a vacuum to carry the vibrations. Now, within an ear, the sound waves will cause the eardrum and other parts of the ear to vibrate, and this is what causes the sensation of sound. Now, this conversion of sound wave to vibrations of solids only works over a very limited frequency range, and this is why the frequency range of normal human hearing goes from 20 Hz to 20 kHz or 20,000 Hz. We should recognise that if we have a high frequency sound, we refer to that as a sound with a high pitch. If we have a high amplitude sound though, we call this a loud sound. If we think about the ear in a little bit more detail, when the sound waves enter the ear canal, they cause the eardrum to vibrate. Now the ear has 3 small bones that will transmit these vibrations from the eardrum to the cochlea. These vibrations will produce electrical signals which get passed onto the brain, which then interpret the signals as sound. Ultrasound waves have a frequency above the range of human hearing, so above 20 kHz or 20,000 Hz. Now ultrasound has so many uses. These include imaging of fetuses or other parts of the body, cleaning jewellery or other objects, breaking down kidney stones, can also be used to detect cracks in pipes. And the important property of ultrasounds that enables us to use it for all these purposes is that ultrasound waves get partially reflected when they meet a boundary between two materials. Let's have a look at how ultrasound can be used for medical imaging. So the transducer in the ultrasound scanner will emit and detect the ultrasound. We're going to put the scanner on the skin and move it across the skin. Now, the ultrasound waves will travel through the body, but when they reach different boundaries between different tissues, they're going to get reflected. Now, these reflected waves will then get detected by that transducer. The time that it takes for that wave to return is recorded, and we can now calculate the distance travelled using distance equals wave speed times time, because we can be familiar with the wave speed of ultrasound. So once we get this distance, we need to think that actually that is the distance that it takes to leave the transducer, go to the object, and then go back and get detected. So the distance to the object is half of what we calculated. So we're going to halve that distance that we calculated to find the depth. Now lots of these measurements are going to get taken by the computer and it will generate an image. Earthquakes produce P waves and S waves. Now, the curved path of seismic waves, like you can see in the diagram here, shows the density of the Earth is gradually changing. As S waves can't travel through solids, they don't get detected on the opposite side of the Earth to the earthquake. And this tells us that there is a liquid core to the Earth. So that's a really important bit of information that seismic waves have taught us about the inner structure of the Earth. Let's remind ourselves of the properties of the two different types of seismic waves, the P waves and the S waves. P waves are longitudinal, they are faster, and they travel through solids and liquids. Whereas S waves are transverse, they are slower, and they travel through solids only. The way that I like to remember which one is which is I remind myself that S wave is transverse, which has a load of S's in it. It is slower, which has an S, and solids only is also an S. So that's my little prompt as to which one is which. We've just seen that P waves travel through both solids and liquids. However, there are still some regions where no P waves get detected, and we call these shadow zones. These shadow zones are caused by refractions between all of these different layers, and they actually tell us that we must have a solid inner core as well as that liquid outer core. So make sure you understand that the study of seismic waves has given us lots of new evidence that's led to discoveries about parts of the Earth which we cannot observe. Echo sounding is another technique that we use ultrasound for. We use high-frequency sound waves to detect objects in deep water and also to measure water depth. Let's have a look at how it works. Let's see how echo sounding is used to find the depth of underwater objects. So this is often referred to as sonar, and this uses ultrasound to detect objects that are underwater. So we emit an ultrasound wave, so a high-frequency sound wave. The wave will get reflected from the bottom of the seabed or the object that we're detecting. We record the time it takes for the wave to return, and we calculate the distance travelled using distance equals wave speed times time. Now, because of course that distance is the distance there and back, we then halve the distance to find the depth. Electromagnetic waves are transverse waves that transfer energy. They form a continuous spectrum, which means that they're just one giant range of waves with varying wavelengths and frequencies. As you can see down here in this diagram, we've got this long wave which goes from radio wave to microwave to infrared to visible light to ultraviolet to X-rays to gamma rays. Now we need to know these in order. Okay, now there's a mnemonic that can help us do this. There's loads of mnemonics actually. I'm going to give you one, but by all means make your own or find one that you really like. I like to use this one, which is that rabbits meet in very ultra expensive gardens. Absolute nonsense, but if it can help place our different electromagnetic waves in order, then that's all I care about. We need to know that the radio waves here have the longest wavelength, the lowest frequency, and the lowest energy of all of these waves. Whereas on the other end of this spectrum, the gamma rays, we have the shortest wavelength, the highest frequency, and the highest energy. So make sure that you learn all of these and you know their properties. You know that they're transverse waves, they transfer energy, and they all travel at the same velocity through a vacuum or air. Different substances may absorb, transmit, refract, or reflect electromagnetic waves in ways that vary according to the wavelength of those waves. If the electromagnetic wave changes velocity when it moves from one substance to another, it will be refracted, and this changes its direction. As you can see in this diagram here, we might need to use ray diagrams to show refraction. The angle of incidence and the angle of refraction are always measured from the normal, not from the surface. Make sure that you never forget that. That's true for reflection and refraction. We always measure that angle from the normal. Wavefront diagrams can be used to explain refraction in terms of the change of speed that occurs when a wave travels from one medium to another. Wavefronts are simply imaginary lines that are drawn perpendicular to the direction that the wave is travelling. If a wave slows down, you can see that when it crosses that boundary, the wavefronts become closer together. However, if a wave crosses a boundary at an angle, then we notice that one end of the wavefront will change speed before the other, and this is what changes the wave's direction. Radio waves can be produced by oscillations in electrical circuits. When radio waves get absorbed, they can create an alternating current with the same frequency as the radio waves. This means that radio waves can themselves induce oscillations in an electrical circuit. Electromagnetic waves can be generated or absorbed because of changes in atoms and the nuclei of atoms. When the electrons in an atom will move down energy levels, as you can see in this diagram, they will emit electromagnetic waves. Now, some electromagnetic waves are more hazardous than others. For instance, UV rays, X-rays, and gamma rays can all have hazardous effects on human body tissues. The effect that they will have depends on the type of the radiation and the size of the radiation dose. Radiation dose is a measure of the risk of harm resulting from an exposure of the body to the radiation. Radiation dose is measured in sieverts, and we should know that 1000 millisieverts is equal to 1 sievert, because we'll often have to convert between the units. Electromagnetic waves become more dangerous as the frequency of the wave increases. This table here shows some of the potential dangers that we need to know. So we need to know that microwaves can cause the internal heating of body cells. We need to know that infrared can cause skin burns. Ultraviolet can cause damage to surface cells, leading to skin cancer as well as premature aging. It can also cause damage to the eyes, leading to eye conditions. Now, X-rays can cause mutations and damage to body cells again. And gamma rays can also cause mutations and damage to body cells. We need to know the uses of all of the different types of electromagnetic waves, and we also need to know briefly why they're suitable for their jobs. So we need to know that radio waves can be used for broadcasting, satellite transmissions, and communications. So some of the reasons why it's suitable for these jobs is that it's able to travel long distances in the air, and also longer wavelengths that the radio waves have can bend around obstacles, allowing them to be detected, even if obstacles get in the way. Now, microwaves are used for cooking, satellite transmissions, and communications. The reason why it's so useful for satellite transmissions, for instance, is that it's able to pass through the Earth's atmosphere to reach those satellites. Now, looking at infrared radiation, we use this for cooking, we use it for thermal imaging and short-range communications. Some of the reasons why this is used is because it's able to be transferred quickly to heat rooms and food. Next up, we've got visible light, which of course includes all the colours of the spectrum, the visible spectrum: red, orange, yellow, green, blue, indigo, violet. Visible light can be used for vision and photography. And because it's a shorter wavelength than the radio waves, microwaves, and infrared, it can be useful for things like fibre optic communications, where, due to that shorter wavelength, it's able to carry more information. Now let's look at ultraviolet. So we use this for security marking, fluorescent lamps, and disinfecting water. Now, ultraviolet radiation has more energy than visible light, and some chemicals used in fluorescent light bulbs can absorb UV light and emit visible light. X-rays can be used for observing the internal structure of objects, such as medical X-rays and also airport security scanners. So the good thing about X-rays is that they can pass easily through skin and flesh, but they can't pass through denser materials like bone, and that's what enables us to use X-rays for medical imaging. Finally, gamma rays. These are used for sterilising food and medical equipment, and also for treating and detecting cancer. Now, gamma rays are the highest energy of all of the electromagnetic waves. And because they're very high energy, they can kill cancer cells and bacteria, making them great for these uses. A lens is able to form an image by refracting light. Now we get two different types of lenses. We have convex lenses, like you can see in this diagram, and concave lenses that we'll have a look at in a moment. But here we have a convex lens. Now, dependent on the position of the object that we're trying to focus, convex lenses can produce images that can be real or virtual, magnified, so bigger, or diminished, smaller, and the images can be upright or inverted, so upside down. Now, a real image is an image that can be projected onto a screen, whereas a virtual image is an image that cannot be projected onto a screen. Convex lenses are thicker in the middle than the edges. They converge the light. So if we have a ray diagram, like we have here in this diagram here, the convex lens gets represented by this vertical line that we see here with outward facing arrows. They're pointing outwards. Convex lenses will focus these parallel rays of light at a principal focus, as you can see just here. All of these rays are passing through that point, the principal focus. Now we call the distance between the lens and the principal focus the focal length. Make sure that you know how to label these diagrams and you can identify how we represent the convex lens using this straight vertical line with these outward facing arrows. Concave lenses, on the other hand, look like this. You can see that they're fatter at the ends and thinner in the middle. Now, unlike those convex lenses we just looked at that can form all different types of images, concave lenses will only form upright, diminished, and virtual images. Remember that a virtual image is one that cannot be projected onto a screen, and a diminished image is one that is smaller than the object that formed it. Now, like we saw there, concave lenses are thinner in the middle than at the ends, and concave lenses will diverge parallel rays of light. Now, if we have a ray diagram like we have here, concave lenses are drawn as a vertical line with inward pointing arrows this time. Now, the rays will separate after passing through the lens, as you can see here, but they appear to be coming from this principal focus. Principal focus is going to be the focal length distance away from the lens. Magnification is the ratio between the image height and the object height. So the formula that we will need to use to find the magnification is image height divided by object height. Now, because it's a height divided by a height, magnification doesn't have any units, though it is very important that you know that we need to be consistent with the unit for the image height and the object height. Can't use centimetres for one, millimetres for another. Make sure you're consistent and use centimetres for both or millimetres for both. All of the colours of the visible light spectrum have their own narrow band of wavelength and frequency. Remember, these colours are red, orange, yellow, green, blue, indigo and violet. Now, in terms of reflection, we can get two different types of reflection. We can have specular reflection, which is reflection from a smooth surface, which is in a single direction. Or we can have diffuse reflection, which is reflection from a rough surface, which will end up scattering. Now, objects can be transparent, they can be translucent, or they could be opaque. Transparent objects will transmit visible light. Translucent objects transmit visible light, but the light rays will be scattered and reflected. And opaque objects do not transmit visible light, but they will absorb and reflect it. Now, the colour of an opaque object is determined by which wavelengths of light are more strongly reflected. Any wavelengths that don't get reflected will get absorbed by the surface. So if we had a white object, all wavelengths of light are reflected equally. A black object, all of the wavelengths are absorbed and no wavelengths of light will get reflected. If we had, for instance, a red object then, the red light will be reflected and all the other wavelengths of light will be absorbed by the surface. If we now think about filters, if we pass white light through a coloured filter, all of the colours will be absorbed by the filter except the light that is the same colour as the filter. Again, remember all of those colours of this white light spectrum. We've got the red, orange, yellow, green, blue, indigo, violet, as you can see here. So if we had a red filter, only red light will be transmitted, and the orange, yellow, green, blue, indigo, and violet colours of light will all be absorbed by that filter. We can think this through with any colour filter. If we had a yellow filter, only the yellow light would be transmitted, everything else would be absorbed. And so we can work that out for any example that they give us. Now we need to know that all bodies, no matter what their temperature, will emit and absorb infrared radiation. The hotter the body, the more infrared radiation it will radiate in any given time. Now, the intensity and wavelengths of light that get emitted will depend on the temperature of that body though. That brings us to thinking about perfect black bodies. A perfect black body is an object that will absorb all the radiation incident on it, and it does not reflect or transmit any radiation. So a perfect black body is a perfect emitter because a black body does not reflect or transmit any radiation at all. Now remember, when we talk about a body, we're just talking about an object. Don't let that confuse you. Now we might be asked, how do we investigate the amount of infrared radiation absorbed or radiated and how it depends on the surface? We could place a Leslie cube on a heat-resistant mat. Now Leslie cubes have 4 different surfaces. They have a matte black surface, a matte white surface, a shiny black and a shiny silver surface. Now we're going to fill that Leslie cube with boiling water, almost up to the top, and we're going to leave it for 1 minute to warm up. We're then going to get an infrared detector to measure the intensity of infrared radiation from those 4 surfaces. Or alternatively, we could measure the temperature of each surface. When doing this, we need to make sure that the detector is the same distance from each surface when taking measurements. This is because the radiation will change with distance. So what we would expect to observe here is that the matte black surface will radiate the most infrared, followed by the shiny black, the matte white, and the shiny silver. So from all this, we need to conclude that all bodies will emit and absorb infrared radiation. However, shiny silver and white surfaces are the worst absorbers, and this is because they reflect all of the visible light wavelengths. Now, poor absorbers are also poor emitters, whereas good absorbers are also good emitters of radiation. Bodies at a constant temperature will absorb radiation at the same rate that they emit it. If the temperature of the body increases, this is because the body absorbs radiation faster than it is emitting it. Hotter objects will emit more infrared radiation in a given time. Now if we think about the Earth's temperature depends on several different factors. These include the rate of absorption of radiation, the rate of emission of radiation, and also the reflection of radiation into space. Make sure you know those 3 factors. This topic starts nice and simple. We remind ourselves that magnets have north and south poles, North poles get represented by an N and south poles represented with an S. We should know that magnets will attract magnetic materials such as iron, steel, cobalt and nickel. We should know that like poles will repel and different poles attract. And of course, don't forget that magnetic forces are examples of non-contact forces. Permanent magnets produce their own magnetic field, which will always be there. Induced magnets, however, become magnetic in a magnetic field. Well, what is a magnetic field that we're talking about? Because we're going to use this concept a lot in this topic. A magnetic field is a region around a magnet where a magnetic material or another magnet will experience a force. And we represent these magnetic fields using magnetic field lines. We need to be able to draw and recognise the magnetic field pattern around a bar magnet. This diagram here shows it perfectly. So we will see that magnetic field lines will always point from north to south. This is really important. The closer the field lines, the stronger the field. And the magnetic field strength, you'll notice, certainly because they're closer together in this diagram, is at its strongest near the poles. As we move away from the magnetic field strength decreases. In the exam, we might be asked how to plot a magnetic field, and we can do this using magnetic compasses. So our first step is you're going to place the compasses around your magnet on a piece of paper. We will then mark the direction that the needle points onto the paper, and then finally we join these points together, and this will show the field lines. Magnetic compasses that we use to work out direction actually contain a small bar magnet. And when these magnetic compasses are not near to another magnet, they're actually going to line up with the magnetic field of the Earth. And this is really important because this tells us that the Earth has a magnetic core. It tells us that it's made of a material which is magnetic. Now actually the geographical south pole of the Earth is actually the magnetic north pole and vice versa. When a current flows through a conducting wire, a magnetic field gets produced around that wire. As you can see in these diagrams, they form little concentric circles around that wire. And the strength of the magnetic field that gets made depends on the size of the current going through the wire. So the bigger the current, the bigger that magnetic field, and also the distance from the wire. The closer to the wire, the stronger that magnetic field, and the further away you get, the weaker it becomes. We can also increase the strength of the magnetic field made by a wire by curling it into a solenoid, which looks just like this. The magnetic field around a solenoid actually ends up being very similar to the magnetic field around a bar magnet. The diagram here shows what that magnetic field around a solenoid looks like. You can see that inside the solenoid it is strong and uniform. We can see it's uniform because the magnetic field lines look evenly spaced. And we can also see that they're close together inside that solenoid, which is what shows that it's strong. The magnetic field is stronger inside the solenoid compared to outside because all of the small magnetic fields caused by the current in each of those turns will add up, causing a greater overall magnetic field. If we wanted to increase the strength of the magnetic field around a solenoid even more, we can add an iron core, and this makes an electromagnet. You may be asked in the exam, what are some advantages of electromagnets compared to other magnets? So one of the really important differences is that we can switch electromagnets on and off, simply by turning that current on and off. Now, you might think, why would this be useful? But if we look at the diagram here, imagine we're in some scrapyard or we're moving around old scrap cars or something. It's much easier if we can use this magnetic force, turn on the electromagnet, attract our magnetic materials and move them using that force, and then turn it off and release them. Another great advantage of electromagnets is that the strength of the electromagnet can be adjusted simply by changing the current. If we increase the current, we get a stronger electromagnet. Whereas if we have a permanent magnet, the strength of that magnet is just the strength of that magnet. We might see some applications of electromagnets come up in the exam. So let's have a look at this specific example of an electric bell and let's see how electromagnets can work. Now looking at this, if we close the switch, we will turn on the electromagnet because the current can flow through the circuit. Now of course, looking at the diagram, you can see we've got this iron armature. This is going to get attracted to the electromagnet, and this is going to pull the hammer towards the bell, and they're going to hit each other and it's going to sound the bell. However, of course, when this happens, we've broken the circuit, and that turns off the electromagnet. This means that the armature is no longer attracted towards the magnet and it's going to move back to its original position. But by moving back to its original position, it's completed the circuit again. And so we're going to have this process just go back and forth, back and forth, back and forth on repeat, sounding that bell. Now this is one application. We could see loads of other ones too. So we just need to make sure that we can apply these principles to any little example they might give us. When we place a conductor carrying a current in a magnetic field, the magnet and that conductor will exert a force on each other. And this force causes a motion. Now this is something that we call the motor effect, and it is a really important phenomenon. So we might ask ourselves, well, how can we increase this force acting on this wire? We could increase the size of the current in the wire or the object, or we could increase the strength of the magnetic field, and those are the two factors that we need to consider. Fleming's left-hand rule is a really handy trick that is going to help you work out the direction of any force on a current carrying wire in a magnetic field. So first things first, and I know that I was always getting this wrong myself, make sure you always pull out the right hand. You need your left hand. So as soon as you get started on this, always double check yourself. Is it my left hand? So now that you've got your left hand out, point them in the direction that you see in the diagram. So your thumb going up, pointing your forefinger, your first finger, and then your second finger sort of going to the side. But the key thing is that these all need to be at right angles to each other, okay? So don't be really lazy with it and sort of not completely point them as you see in the diagram here. So your thumb tells us the motion or the force. First finger tells us the field, and the second finger tells us the current. Now in a question, you'd normally be given two of these and asked to find the third. So line up the two that you know about, and then the third finger or thumb is going to tell you the direction of the thing that you're being asked about. Now, really important here, they won't always tell you, oh, the current is pointing this direction. They might instead have a positive and a negative, and they expect you to know that the current flows from positive to negative. Next, let's think about the magnetic field. Again, they might not tell you the direction of the field lines. Instead, you might have a magnetic north and a magnetic south, and then you need to know that the field lines will point from north to south. So those are my top tips there. Make sure you use your left hand most of all though, because I think that is the most common mistake. A current carrying coil of wire in a magnetic field will actually rotate. So what you see here in this diagram will rotate. Now this is how electric motors work. What we would need to do is use Fleming's left-hand rule on both this side and also this side of the wire. The reason why we would want to do this is because we can work out the direction that the pink bit of the wire is pointing and that the blue bit of the wire is pointing. So if we look at this pink part first, you can see that the current is pointing in this direction here. You would need to take your second finger, which is the current finger, and point it in that direction. Then you can see the field lines aren't shown on this particular diagram, but we know that they go from north to south. So now we want to make sure that our first finger, field, is pointing in that direction. Now if we do this, we will see that our thumb is pointing upwards. And as you can see, the arrow is already here, but that's really important. Now let's do the exact same bit on the bit that I've highlighted in blue, the part of the wire nearer to the South Pole. So in this case here, let's clear some of these off. In this case here, you can see that the current is actually going in the opposite direction. It is now going away from us. So our second finger needs to point in that direction now, but the field is still pointing from north to south. So we've got our first finger pointing from north to south. Our second finger is pointing away from us and into the page. And our thumb should be pointing downwards. That tells us that we have a downward force on that part of the wire. If you didn't get those right, the main little troubleshooting tips that I would say is make sure that your fingers and thumb are all at right angles to each other. Make sure you are actually using your left hand, and make sure that you're assigning each finger and thumb the correct quantity. So remember, your thumb is your motion or your force, first finger is your field, and your second finger is current. So in this case, I can see that as it's going up here and down here, it is moving in the clockwise direction. And that will be a common question in an exam. So in an electric motor, we need to know what the role of a split ring commutator is. So split ring commutators reverse the direction of the current every half turn. The importance of this is it ensures that the coil continues to rotate in the same direction. We might also be asked what's the role of the graphite brushes that we can see here. Well, these are of course electrical conductors. You should remember that from chemistry. And they complete the circuit as the wire rotates. However, they're not having permanent contact. Imagine if it was an actual cable that was permanently connected to this loop. And it's spinning and it's spinning and it's spinning. It's going to become a massive big old jumble, isn't it? Whereas what we have instead are these brushes which have permanent contact with the loop, but they're not having to move all the way around with the loop as it rotates. And so that makes it work perfectly. They complete the circuit as the wire rotates and makes this work. Now this equation will be a big one on calculations in this topic. So the magnetic flux density is a measure of the strength of a field. If we had a current carrying wire, which is at right angles to a magnetic field, just like we've been seeing in these motor effect questions, force exerted on it will be calculated by multiplying the magnetic flux density, which is measured in Tesla, which is capital T, times by the current, times by the length. And it's that simple. That's how we work out force on a current carrying wire in a magnetic field. We just take the magnetic flux density, times it by current, times it by length. Loudspeakers and headphones work in a similar way in that they use the motor effect to convert the variations in current in an electrical circuit into pressure variations of sound waves. So let's describe the steps as to how loudspeakers and headphones work. So, first of all, we have a coil of wire and we place it inside a permanent magnet and attach it to a diaphragm. So the current's going to flow through the coil and the wire is going to experience a force due to the motor effect because we've got this current carrying wire in the presence of a magnetic field. As a result of this, the diaphragm will move. Now, because we have an AC or alternating current here, it's changing direction the whole time. And as the AC current changes direction, the direction of the force produced by that motor effect is going to change as well. This causes the diaphragm to move back and forth, causing it to vibrate. Now, these vibrations will cause variations in the pressure of the air and will form a sound wave. And importantly here, the frequency of the sound wave produced is going to be equal to the frequency of the alternating current. We can induce the potential difference across the ends of a conductor if there is a changing magnetic field around the conductor, or if the conductor is moving relative to the magnetic field. And this can be done in one of two ways. We can move a wire in a magnetic field, or we can do the opposite. We can move a magnet in and out of a coil of wire. In both of these cases, we have this relative movement between that conductor and the magnetic field. Now, if we have a complete circuit here, then a current will be induced, and this is what we call the generator effect. Now, in the exam, it's very common for us to be asked how we can increase the size of the induced current or potential difference. So we can increase the speed of that movement, we can increase the strength of the magnetic field, or we can increase the number of turns on the coil. Another very, very common question is us being asked how we can reverse the direction of that induced current or potential difference. And in this case, we can reverse the direction of the movement of the wire or the magnet. So for instance, instead of inserting the magnet into the coil, you could remove the magnet from the coil. Or we could reverse the polarity of the magnet. So instead of putting the north in, you could put the south into that coil. And those are our two ways that we can reverse the direction of the induced current or potential difference. Make sure you know all of these facts because they are very common questions. The generator effect has different uses. It can be used as an alternator to generate an alternating current, or it can be used in a dynamo to generate a direct current. So we need to make sure that we know the difference between alternators and generators. Well, here we have an alternator. An alternator is an alternating current generator. A simple alternator is made up of a coil of wire which rotates in a magnetic field, so this could be it's placed between two magnets. Now, the ends of the coil are connected to these slip rings that we can see in this diagram. These slip rings are really important because we ensure that we have a continuous connection with the coil, and it allows the current to flow from the coil via those graphite brushes, which are maintaining that connection, into the circuit. And in this case, you can see that it's going to light up a lamp. Alternators get used in cars to keep the battery charged. Now this graph here shows the induced potential difference in an alternator against time for one complete cycle. You should be able to see here that the current and the potential difference change direction every half turn. You might be thinking, well, how does this tell us that? But the direction refers to whether the axis is positive or negative. So what we see here is in this first half of the cycle, it's moving in one direction, and then in the second half of the cycle, it moves in the opposite direction, and we can see that on the graph because we're in the negative y-axis. We could get asked in an exam, how can we increase that maximum potential difference? So how could we make this curve have a greater amplitude? Well, a way that we could do this is we could increase the rate of rotation, we could increase the number of turns on the coil, or we could increase the strength of the magnetic field. So make sure that you know how we could increase the maximum potential difference in an alternator. Now let us have a look at this graph in more detail, this graph of induced potential difference against time. And of course we can see that at different points of the graph, it goes up and then down and then back to zero again. Let's look at these bit by bit. So when the coil is at 0 degrees, so here, what we would observe, of course, is that the coil is moving in the same direction parallel to the direction of the magnetic field. Now no field lines will get cut then, and so no potential difference is induced. Whereas now when we have a look at when the coil is at 90 degrees, what is happening is the coil is moving at right angles to the direction of magnetic field. It's cutting it as much as possible in that case, and a maximum potential difference is induced. Next up in our rotation, we're now at 180 degrees. And again, this is still parallel to the direction of the magnetic field. No field lines are going to get interacted with, and so no potential difference is induced. Now we get to the next step, 270 degrees. At this position, the coil is moving at right angles perpendicular to the direction of the field again. So again, we've got this maximum amount of field lines being cut, and so a maximum potential difference being induced. However, it's in the opposite direction, isn't it? Whereas when it was at 90 degrees, it could be left to right. Now it might be right to left. And so we induce a potential difference which is at a maximum in the opposite direction to when it was at 90 degrees. Finally, we end up back at 360, which is essentially the exact same orientation that we had before when we were at 0 degrees. We're moving parallel to the direction of the field again, and no potential difference is induced. A dynamo is another use of the generator effect. Dynamos are direct current generators this time. Now, as you can see in this diagram, dynamos use a split ring commutator instead of those slip rings that our alternator did. Now, the importance of this split ring commutator is that it's going to make the ends of the coil swap contacts with the circuit every half turn. And the importance of this is it ensures that the current will always flow in the same direction relative to the magnetic field. And it's this that makes them generators of direct current rather than alternating current. An example of a use of dynamos is in some bicycle lamps. So as you're on your bike and you're pedalling away, the light will light up. And that is because these bicycle lamps might have a dynamo within them that generates electricity while you cycle. Now this graph here shows the induced potential difference in a dynamo against time for one complete cycle. Make sure that you can draw this and the one for alternators as well. And the main feature here is that for every one cycle, the induced potential difference varies from 0 to a maximum, back down to 0, and it does that twice. What you notice here is that the potential difference will always stay in the same direction. It never goes into negative potential differences, which is the direction of that potential difference. Always positive, which means it always stays in one direction. If we want to increase the maximum potential difference in a dynamo, we do exactly the same things that we would in an alternator. We can increase the rate of rotation. This would also squash this curve, bringing the maximums closer together. We can increase the number of turns on the coil, or we could also increase the strength of the magnetic field. So make sure you know those three and the effect it would have on your curve. Finally, let's have a look at the curve again for dynamos. Let's have a look at what's happening at each position. Now this is really similar to the one for alternators. Again, when we're at 0 degrees and the coil is in the same direction, parallel to the direction of the magnetic field, we have no potential difference induced. They're travelling in the same direction, so there's no cutting of the field lines. Whereas when we get to this maximum potential difference, the coil is at right angles to the magnetic field. And so that means that we're going to get a maximum amount of these field lines cut with this wire, and a maximum potential difference is induced. Now at 180 and 360, just like at 0, our coil moves parallel to the direction of the magnetic field, and therefore no potential difference is induced. However, when we're at 270 degrees, just the same as at 90 degrees, we're moving at right angles to the direction of the magnetic field again, and therefore we get that maximum potential difference. Notice that unlike with the alternator, we're not moving in the opposite direction, and that's because in the dynamo we had that split ring commutator which swapped the contacts every half turn. Microphones make use of the generator effect to convert the pressure variations in sound waves into variations in electrical current. So let's describe the steps as to how microphones work. First things first, we attach a coil to a diaphragm. The coil is then placed inside a permanent magnet, and the pressure variations in the sound waves cause the diaphragm, and therefore the coil it's attached to vibrate. Now that coil is now moving relative to the magnet, and this induces a potential difference in the coil. If the coil is of course part of a complete circuit, then a current can flow around that circuit. The key fact is the fact that the frequency of that induced alternating potential difference is going to be the same as the frequency of the original sound wave. Transformers are made up of two coils, a primary and a secondary coil, wound around an iron core. Now the whole job of a transformer is it can change the size of an alternating potential difference. We can scale it up or scale it down depending on what we're using it for. So we need to be able to recognise what one of these transformers looks like we see in the diagram here, be able to label it, and also understand why we use an iron core rather than another metal. And that's because iron is magnetically soft, which means that it can be easily magnetised and demagnetized. Here we have a really important equation that we're going to use with transformers. We need to know that the ratio of the potential differences across the primary and secondary coils is dependent on the ratio of the number of turns on each coil. So here we have Vp, so the voltage or potential difference on the primary coil, divided by the potential difference on the secondary coil, is equal to the number of turns on the primary coil over the number of turns on the secondary coil. Now, the thing with this is you need to identify what belongs to the primary, what belongs to the secondary when substituting them into the equation. And my top tip for this is remember that you can write this equation upside down. So you can have Vs over Vp equals Ns over Np. That can be really helpful when it comes to rearranging because it just simplifies it. If you had to find out what Vs is or Ns, make sure you write this upside down so that those are on the top. It's much easier to rearrange. We need to be able to recognise the difference between a step-up and a step-down transformer. Step-up transformers have more turns on the secondary coil. I imagine it literally like I'm stepping up, and so I'm going from less to having more. And when the turns increase, so does the potential difference. So the potential difference across the secondary coil is more than the potential difference across the primary coil. Step-down transformers is just the opposite. And here I think of it as, again, like I'm stepping down. The secondary coil has less turns on it than the primary coil. And therefore, as a result of that, the potential difference across the secondary coil is less than the potential difference across the primary coil. So turns and potential difference follows the same pattern. Now, if the transformers that we have are 100% efficient, which of course really doesn't generally happen, but for the sake of GCSE physics, this is what we assume. 100% efficient, the electrical power output is equal to the electrical power input. And this here is the equation that we use. So power output equals power input, but we'll use that in terms of the equation that power equals V times I. And we say that Vs times Is equals Vp times Ip. And this of course means that the potential difference of the secondary coil times by the current in the secondary coil is equal to the potential difference in the primary coil times by the current in the primary coil. So we've seen all the maths there, but now we need to have a look at how transformers work. We need to be able to describe all of the steps as to how transformers work. So, first step, primary voltage supplies an alternating current to the primary coil. Next, this alternating current induces an alternating magnetic field in the iron core. So the current never flows in that iron core. Instead, that magnetic field that we've just induced is what's able to move through it. And of course, as it's moving through that core, it moves from where the primary coil is to where the secondary coil is. And that alternating magnetic field induces an alternating potential difference in the secondary coil. Now that we've got this induced potential difference, that produces an alternating current. And so those are 4 key steps that we need to know to describe how transformers work. As a final little reminder here and a top tip, don't forget that transformers will only work with an alternating current. If we connected them to a direct current like a battery, they would not work. We need that alternating current of a main supply. Our solar system is made up of one star, the Sun, 8 planets, which are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. There are also dwarf planets which orbit the Sun, as well as natural satellites such as the Moon that orbit planets, not just the Earth. Other planets, as you can see in this diagram, also have their own moons as well, but we don't need to know those in detail. So our solar system is actually a part of the Milky Way galaxy. It's a tiny, tiny little dot compared to the rest of the galaxy. Galaxy contains billions of stars, and think about it, our solar system has one. The life cycle of a star is dependent on the size of the star. Now, to start off with, before the star becomes a main sequence star, all stars go through the same processes, and then it goes off on a little tangent. Let's start by having a look at what the initial life cycle of a star is. So to begin with, we have this cloud of dust and gas, which is called a nebula. All of these dust and gas particles get pulled together due to gravitational attraction, and we have a protostar form. Now this protostar gets further pulled together by gravity, and as it gets pulled together, the particles in the protostar collide together more frequently. Now when this happens, we see more energy transferred from the gravitational potential energy store to the thermal energy store of these particles, and as a consequence, we see the temperature increase. Now, when this protostar gets hot enough, nuclear fusion of hydrogen nuclei begins to occur. This causes helium nuclei to be formed, and huge amounts of energy is released. So all of this energy release causes a high pressure within the star, which causes an outward force. We also have that inward force, gravity. Well, for a certain point, these forces are going to be balanced, and so the star is stable. Now we call this a main sequence star. So now that we've reached the main sequence, what happens next is going to depend upon the size of that star. If we have a star about the size of the Sun, then what will happen is after the main sequence, we will form a red giant. Now this happens because over time, all that hydrogen that we were fusing together is going to get used up. And now we just have a larger proportion of larger nuclei. As a result of this, the star expands, and that's when we have this red giant. Now, over time, eventually, not only the hydrogen will run out because everything's fused together, but everything's going to start to run out, and the nuclear reactions begin to stop. When fusion stops, we don't have that pressure acting outwards. And so we only have this gravitational force acting inwards. So when the nuclear reactions stop, the star will contract and it becomes a white dwarf. Eventually, all of the thermal energy that that star once had has been radiated away, and the white dwarf is going to cool down, eventually becoming a black dwarf. However, if we had a star that was larger than the Sun, we will see that after it stays on the main sequence for a long period of time, it will become a red supergiant. After that, it's going to explode in a supernova, and it will either become a neutron star, or if the star was particularly massive, it will become a black hole. These nuclear fusion reactions that occur in stars are responsible for the production of all naturally occurring elements that we're familiar with. Of course, the hydrogen nuclei fuse together to form the helium nuclei. And then there's more fusion reactions occurring in stars with large masses that form other small nuclei. And then eventually, when the star becomes a red giant or a red supergiant, we will see that helium and other small nuclei will fuse together to form larger nuclei. Elements that are heavier than iron get formed in a supernova. And of course, a supernova is that explosion. And during that explosion of the supernova, it's going to distribute those elements all over the universe. And that's how they ended up on the planet Earth, for example, for us to use. Objects orbit other objects or bodies due to gravity. And gravity provides that attractive force between the two of them. We need to know a little bit about these different types of orbits. So we need to know that the Moon orbits a planet, and it has a circular orbit. We need to know that planets orbit the Sun and they have an almost circular orbit. And artificial satellites, of course, whereas the Moon is a natural satellite, artificial satellites orbit the Earth or any other body in the solar system that might be of interest, and it has a circular orbit too. We need to know that when an object orbits a body in a circle, it is orbiting at a constant speed. However, the direction of its motion is constantly changing. Now, because velocity is a vector that has both magnitude and direction, although the magnitude of the velocity, its speed, is staying constant, the fact that it's changing direction tells us that the velocity must also be changing. For a constant velocity, it needs to not only have a constant magnitude, but it also needs to stay moving in that same direction. Now, the force due to gravity depends on distance. So the smaller the distance between any two bodies, the bigger their gravitational attraction. Now, the bigger the force of gravitational attraction, the bigger the acceleration of the object in orbit, because force and acceleration are linked. Now, a bigger acceleration will mean a greater change in the velocity. Now, objects in small orbits travel faster than objects in large orbits. Now, this must mean that to change the orbital speed, we must change the radius of the orbit to ensure a stable orbit. If a wave source moves relative to an observer, we will see a change in the observed frequency and wavelength. And we all have everyday examples of this. If we think of an ambulance or a police car or something, as it moves towards us or away a bit, we're aware that it sounds different. So, as the wave source, that police car, moves towards an observer, as you can see from this diagram, the wavelength will decrease and the frequency will increase. And that enables us to hear this higher pitched sound if a police car is coming towards us. However, as the wave source moves away from an observer, the wavelength will increase and the frequency will decrease, giving us a lower pitched sound. Now, this isn't just something that's useful for making sure we know where ambulances and police cars are. It can also tell us a lot about galaxies. So, when we observe light from distant galaxies, we can see that there is an observed increase in the wavelength of light from the most distant galaxies. In fact, the further away those galaxies, the faster they are moving, and the bigger that observed increase in wavelength. Now, we call this phenomenon redshift, because the wavelength is getting shifted into the red end of the spectrum, the longer wavelength end of the spectrum. Now, since 1998, scientists have observed light from supernova that suggests that distant galaxies are receding even faster. And this all comes down to providing us with some evidence for something called the Big Bang Theory. This redshift is the observation of redshifted light when observing distant galaxies, and it shows that the universe must be expanding. Now, the Big Bang Theory is the theory that the universe was once a very small, extremely hot, dense region, and a giant explosion occurred, which caused the universe to expand. And that redshift of light from distant galaxies provides us with evidence to support the Big Bang Theory. However, we have evidence for the Big Bang Theory, and most scientists assume that this is the likely way that the universe formed. However, there are many things about the universe that scientists still don't understand. We don't need to know about these in detail, but we just need to know their names. We need to be familiar that scientists still don't fully understand dark mass and dark energy.
Ouch! This is why in some videos I'll explain scratches.